Hi, my name is Alusain Barry. Welcome to this lesson on calculus on the product rule for differentiation. Earlier, we dealt with different rules and techniques for differentiate for finding the derivatives or the differential coefficients of different functions. Today, we are going to focus on finding the derivative for products. You can imagine earlier what we said was the derivative or the differential coefficient of a function, say y defined by x, so y as a function of x um, is the limit as the change happening in x tends to 0 of f of x plus the change in x minus f of x all divided by the change in x. The only thing was that in the earlier we represented this as h. Okay, so that's why I put it here just so you can see. You can imagine this as an average really, or in other words geometrically as a rise over run. Okay, in earlier years you might have come through the gradient because y2 minus y1 divided by x2 minus x1. Okay, so this is something similar we do here. The top of the our equation here is actually defining the change in y. Okay, remember changes in y depend on changes happening in x, so that's why we have x in there. Okay, because y is actually defined by x squared. And then for the run we have changes. Say for example we have um, original y here and then the change in y. Okay, we can represent this. Let's just have drop this down. So we can imagine this was the original x and this is the original y, so xy, and then there is a change in y resulting from a change in x. Okay, so because there is a change in x, now there is going to be a change in y as a result. We can just write this here again. Sorry, we can write this as a change in y. Okay, so this change in y is resulting from changes in x. So this, the change in y resulting from the change in x. So what we are trying to do here, we're finding different points. Imagine there is a tangent we are drawing between the 2 points P and Q here. We are coming closer and closer, so we are reducing the change happening in x closer and closer to 0 without actually making it 0. Right? So that limit we have is what we call the derivative or the differential coefficient of that function. Okay, of course we looked at other methods for finding this. This we found was cumbersome. Many people find it difficult. So instead, what we do is we look for techniques. So that's why we have techniques such as the product rule. Okay, for the rule, you can imagine a product being say 2 times 3. When we multiply two numbers, we have the result is a product. 2 times 3 gives us 6. The only thing is that in this case, what we are multiplying are functions in different variables. It can be x. Okay, a function can be, say for example, y can be defined as a function x cubed multiplied by 2x minus 3 raised to the power 5. This was actually a past question and answer in the further mathematics exams. Okay, you can imagine this as a function and this as another function. Right? So what we try to do, we say let y be equal to uv, right? Where u takes is x cubed and v is 2x minus 3 all raised to the power 5. Okay, so you can now see, so if we do this, we can simply say y is equal to uv. But now uv are functions in x. Okay, so we can do this, we can manipulate this, and then we find the derivative much easier. Okay, so actually let's do an example of this so we can see. Sorry about that. Okay. So now, if we're asked, let's say there is a question asking us, say, differentiate y equals to x cubed, as we have up there, multiplied by 2x minus 3 all raised to the power 5. Okay, I can say solution. Now, as I said, noted earlier here, we can assume this to be, this is a product, okay? Although there isn't a multiplication sign here, but you can tell this bracket indicates multiplication. So this is a product, right? So we say here, let's write our function y is x cubed multiplied by 2x minus 3 raised to the power 5, okay? So we say let y be represented by uv, where u is the function x. So it's almost made up of two different functions, okay? And v is equal to 2x minus 3 all raised to the power 5, right? Um, let's have some space, and then we can now differentiate each of these ones, okay? Well, first of all, let's state the product rule for differentiation. According to the product rule for differentiation, we have dy dx is equal to, if we have such functions, we say the function v, we hold it, and then we multiply it by the derivative of the function u. So du dx, the derivative of u with respect to x, okay? So that is the rate at which u is changing with respect to changes in x, plus now we hold u, the other function, and we say dv dx, the rate at which v is changing with respect to changes in x. Okay, so now we can go on and say, we can go on now. So this is our product rule. Let me just highlight this. This is the product rule for differentiation. Product rule for differentiation. Okay, so this is what you do. You hold the one of the function, you assume y is made up of two functions or more, but in this case we only have two. If you have more than two functions, it's best to multiply them out so they become two different functions, okay? And then what you can do is you find the derivative of each of the functions and then use this formula, okay? So you say dy dx is now equal to v here, which is this 2x minus 3 raised to the power 5 multiplied by the derivative of u with respect to x. And the derivative of u with respect to x is actually, remember when we in our differentiation of monomials earlier, you can go back and check the other videos, we said when we have such a function in the form a raised to the or say x raised to the power n, its derivative dy dx will be equal to, we multiply the function by the power and then we subtract 1 from it. So if we multiply everything by the power, which is n, so we are having n times x, but now we are taking 1 from the n, so n minus 1, okay? In this case, du dx, we are having 3 as the power. So what we are doing, we are going to multiply everything by 3 and then we subtract 1, okay? So therefore du dx is going to be 3x, 3 minus 1 is going to be 2, so 3x squared, okay? And